Hello and welcome to live session 12. Today is the last session and we are starting with problem number 1. So this is actually mono halogenation reaction. So with that it can act as Br dot and generate this particular radical, and in that way it can form this. It can form this thing. So in that way, after that, this dot and Br dot, these two can actually combine and give you the mono bromo product. So this is one of the thing, and next thing would be so after that the bromo compound is formed. So this is one of the way. Another way would be, so this is just the keto form, and enol form also can exist. And after that, this can be generated, would lead to formation of monobromo product. Now next problem is quite easy. So with this TSOH and this particular protecting group, you can just to consider the protection group chemistry. At first this happens, followed by this particular attack. This would lead to this compound. So quite easy. B would be your product, and in this particular thing, potassium tetroxide is accept good base, not good nucleophile. That's why it would do the elimination thing and form this eliminate product C. Now after that, this is a radical generator. Br dot would be forming, and here H can be abstracted, H dot. So in this particular condition, this particular radical versus this radical, so these two protons are available. The things let's not consider. This is the stable one. So now Br recombination will lead to formation of D compound. And with that, it had some interaction with Hc, then Ac minus be attacking here, kind of substitution reaction will lead to formation of compound A. Now after this would do the reduction and make it OH followed by base mediated. This is the this electrophile is nothing but this, and this is the warm protection group. Then this H2PD is actually selective, chemoselectively reduce this part, and it would make compound C. So here it would make actually compound B, because this would be unreacted and this reaction should be there. Now after this, you would be generating, at first you would be generating this kind of compound. Then this is IBN act as radical initiator, it would generate this particular reticle, and after this particular mechanism would follow, SN dot stand in, and this sulfur bond would be forming, followed by this particular type of decarboxylation kind of thing, and it is neutralized by this H dot, and the reticle cycle would go on like this. So that's how the compound the thing would be D, because you just make OH to H. So that kind of reduction. Now with H2O4, this would be the Mondi protection condition, then followed by this BCC oxidation with this particular keto compound. Now they have asked the which is the suitable condition. It would be the weak one, and so C would be the right option. So I hope I am audible. Yeah, seems like it's okay. So welcome all to the live session 8. So today in the same way we will progress. So let's start with the today's first problem. So this is the first problem. So just just a statement that today's problems are mostly based on protection group and reprotecting. So protection group chemistry. So yeah, most of the problems are based on that for today's problem solving series, and so in between, so I will give the some of I will going to describe some of the protecting groups and how they can be protected and they are used. So I will today give an brief overview of this chemistry, and this way we will solve the today's problems. So for the first problem, let's look at. Yeah, so you can see, so these two are actually ketals. This is normal oxygen based, and this is sulfur based. Sulfur based. So as here we have one hydrogen, so they are actually acetal. So acetal ketal protection we will know. So with Hg2 plus, this it can be, we can selectively deprotect only the this type of sulfur partner, not oxygen partner. So this is quite reduced selective for that case, because Hg2 plus you can of course it is a heavy metal, and sulfur Hg coordination would be much stronger than oxygen Hg. So that's why this sulfur centers would react more easily with Hg compared to the oxygen one. So that's why this part would be deprotected first. So in and the second step is the Wittig reaction, and you can see this is a stabilized Wittig, so it would give us an E enantiomer. So that much we can say from the just looking at the reagent. So if we correlate with that, so you can see this oxygen, the A part. So you can see this is unreacted, but in presence of Hg2 plus it is not possible. So A should, that's how we can eliminate. And here for the B case, just as we have discussed that this part is unreacted with Hg2 plus, and this can be reacted. So here also you can see that, and here we also formed an EN answer. So that's why B should be the answer. And for the C case, you can see both sulfur and oxygen based protection are deprotected, which is not possible. So C, that's how we can eliminate. So that's how we can easily solve this kind of problems, and the right answer should be B. So let's look at the mechanism briefly. So this is the oxygen protected partner, and there are three carbons in between, and this is sulfur protection. Now with Hg2 plus, at first what would be happening that this sulfur and Hg, they can easily form a bond, and after formation of this bond, the H2O can easily attack here, or you can think of this kind of elimination also. So main thing is to deprotect. So after let's do it intermolecularly. So this kind of species can be generated, and then again the same way actually this part also can be taken care. So here it is positive, so H2 can attack. So now S is neutral. Now it can interact with another Hg2 plus partner, or this Hg plus itself. It can do the same thing. So that's how this whole part can be flipped. So when that happens, so we would be getting this particular aldehyde. Now this is our Wittig. So we will do the normal Wittig chemistry now. So in this is the reactive form of this type of phosphorus, this type of halides. Now this attack followed by this attack. So yeah, so this type of thing would be forming. So the Wittig part we have AH and CO2 heat. Okay. So now just simple elimination, formation of this phosphine oxide, and here we would be generating one double bond or olefin whose stereochemistry would be selectively E, right? This anti V, and phosphine oxide would be generating. So this is our uh, so this phosphine oxide is the byproduct of this type of reaction. So that's how you can easily solve this. But one thing here, all stereochemistry are E, so that's why we can easily solve this. But you may face some questions where you may ask about this stereochemistry itself. Let's say if you have E stereochemistry and Z stereochemistry, so how you can differ between them. So for this type of Wittig reaction, this specific stereoselectivity is well known. So just let me give a little bit description of that. So here you can see it is unstabilized light. Why it is stabilized? Because this particular negative charge can be easily in resonance with this this functional group. So here it is, as here you can see keto. In our for our question it was a star. So that's how this negative charge can be delocalized with this, and it got stabilization. So here that's how aldehyde or keto or esters are stabilized lights. Here you can see the resonating form, so that's how it got stabilization. What are the unstabilized lights? So normal alkyl groups where this negative charge is completely localized in this particular carbon, it cannot be delocalized over here, so that's why it is unstabilized light. And this is an hard and fast rule or thumb rule you can always remember, that stabilized light always would give E-selective stereochemistry, means this type of olefin, and for unstable light you would always generating Z-selective uh, olefins. So like this. So why is that? So there are some research is still going on, but so with the approach uh, uh, we can do some reasoning why this type of selectivity is coming, or how this type of selectivity is coming. So that can be, so that I am going to discuss now. So let's look at, so this is any light, and this is an aldehyde, or it can be keto, so with whom the light would be reacting. So this is the two molecules. So now you can see, so they are actually reacting in an this this type of viscous fashion, not parallel approach. You can say it is an perpendicular approach, and in this type of perpendicular approach, the molecule or the transition state would always be preferred where the interaction between two bulky groups, for this case it is R group, and this phenyl ring would be minimized. So that's how the molecule or system would prefer to react. So here you can see if the that is the other conformation. So let me, this is the stable one, stable transition state, or you can say stable approach, or favorable approach, and another approach would be, so another approach would be here R, right? So for this particular case, you can see this alkyl group or aryl group, this substituted R is facing an interaction with this huge bulky phenyl ring. So that's why it should be unstable, or not favored. That's why this type of approach should not be favored over this, right? So that's why this kind of approach is favored for this kind of Wittig type reaction. So now what would be happening? The CC bond formation and phosphorus oxygen bond formation. You can see this phosphorus oxygen bond is pretty strong. That's how the reaction is feasible. So that's how this would be forming an intermediate. This four member is intermediate, and from here we all know how things should be going. So this should be generating an G selective product, G stereochemistry. Why? Because you can see when we arrange this, so both are in below fashion. So that's how this can be generated. So from here, one thing we can easily say, so this is a kinetic stable product, or you can say kinetically controlled product, because the product is not stable, but the approach of this transition state is favoring this formation of this particular intermediate. So what is the other intermediate? Other intermediate would be, so let me see, if this kind of approach is happening, so then the formed product should be like this, means they should be in anti. So if phenyl ring is in above, it should be below. So here you can see anti approach, it would generate is stereochemistry, this kind of one. Here we are generating this, so it is TCP approach, and this is TCP approach. So that's how it reagent reacts. Now coming to the key differences between stabilized and unstable light. So look at this particular arrow. It is unstable light, right? Because R it is here alkyl group, no stabilization. So here you can see it is an irreversible act. So it is an irreversible process. But when we look at the stabilized light case, it is an reversible act. Means this can be formed again. The system can driven back to this compound. Means to starting material. So here you can see it is an reversible act, and here it is an irreversible. So that's how we can differentiate between the stabilized case and stabilized light and unstable light cases. So this is irreversible and this is reversible. Now why is it is reversible and it is irreversible? So because you can see when irreversible, for this type of irreversible case, if we regenerate the starting materials here, the light is unstable. So system would not be preferring to form this kind of molecule. But for the stabilized case, you can see it is unstabilized. So that's how the system has a preference over this type of stabilized lights. So now, so it is an reversible error. So the system having this form and this form. Now, for this type of stabilized light case, as it is reversible error, so that's how the system become such that we are having an TCP driven or thermodynamically controlled product which is more stable. So in this particular form, so you can see three species can be possible, but the when this type of stabilized light, and this is for me. So as it is an reversible thing, so system is slowly generating the stable intermediate where the two substituents, ester group and this alkyl group, are in antiphasor. So it is an TCP driven product, or it is a TCP. So that's how when we eliminate the phosphine oxide from this particular intermediate, we will be generating E alkene. So that's how stabilized light are generating E alkene, and unstable lights are generating Z alkene. So that's how things are operating to give us an stereo selectivity. So I hope this you have understand. Now for the next problem. So you can see easily see this is ketal form, right? So it is a ketal form of normal acetone. So in presence of acid, and this is our reagent, or this is a certain material. So if we react these two species, let's see. So in presence of acid at first, one of these OMe can be protonated and another OMe would be directing to leave one methanol group. So this is the reactive species we have, and methanol we have generated. So these all things are reversible. Now in the system we have this molecule. So you can see we have many preferences, but it is a primary alcohol, and others to us secondary alcohol. So here you can say that repulsion or this type of easier or easily approaching this oxygen, or easily available oxygen, it is sterically hindered. So that's why this particular oxygen can be more prone to attack. So that's how this should be first attacking this reactive species and generating the following molecule. So after this attack, we will be generating this species, and here we have weight. So again, H plus system in the system it is readily available, and OM will be reacting, and this oxygen push would do like this, and it again generate, and it would be generating this particular species. Now here you can see we have two options. This OH can attack or this OH can attack. So let's look at both the possibilities. So let's say at first this OH is attacking. So then what species will you generate? Oh, sorry, here one carbon is missing. CH2, this kind of thing. Yeah, so this species, so that's how it will be CH2, it would be O, and this would be generating if this oxygen attack, and if this attacks, then the system would be the distorted system we would be generating. So this kind of species will be generated. So now look at the options, right? So between this and this, we can easily say this would be very much favorable over this because of the strength system, and this is, and also 1 2 3 7 member 6 7 not fused, some rigid thing is there, so definitely this would be more stable than this. So basically we can easily drive the system over this particular product over this. So this can we just that we can eliminate. So this is we are generating, so this is should be one of the answer, and here you can see this is one of the intermediate what we have generated. So this cannot be stable in presence of acid. The second attack would be easily preferred, so we cannot isolate in this form. So that's how the right answer would be A. So yeah, so as I am saying in my starting introduction, that today we are going to do most of the protection and reprotection chemistry. So two key points or two key concepts I am going to briefly discuss. So for oxygen cases, the one of the useful or protection groups are this type of silicon based protection groups. So TMSCl, so TMS are trimethyl, means this kind of silyl fluoro, so uh, this type of silyl protection. So that's a TMS. So let me write it O. So with oxygen, this kind of with alcohols are protected like this type of molecules. You know that stability of oxygen silicon bond. That's why these are these particular things are used. So this is an TMS protection. There are TBS protection also, and here you can see TBDMS protection. So why it is TBDMS? Because you can see one tert butyl group is there. That's how this tert butyl TB came, and dimethyl silyl protection group. That's how TBDMS. And why TMS? Because trimethyl silane. So that's how it is TMS. So that's how the naming came. It is easily, I think, you can go to any book, and you can see the namings. So the most important things are they are all silicon based. So that's the thing. So TMS, TBS, TBDMS. So this kind of protecting group are used in this type of protection group chemistries, and for, so for the this is are for the protection part, because you can see we have these two. So and they are going to do one lithium addition. So if OH is present, what would be happening? This lithium species and this H plus. So at first, this lithium would abstract a proton from here, and it would become polythiated, and this lithium reagent would be OH. Would be just this type of element. So that's why we need to protect this kind of molecules. So in presence of imidazole and it's in DCM as a solvent, we can easily do this type of protection, and then after doing the reaction we can also eliminate that this kind of protection group easily. So that's the thing about the protection groups, we can easily make them and we can easily break them also. So for this type of silylated protection groups, the most famous or useful reagent to protect them are fluoride based reagents, like here you can see tert-butyl ammonium fluoride, this kind of molecule. So here if this F minus, it has this F minus have stronger affinity to the silicon, as you can see this particular electronegative elements have strong affinity towards silicon, like oxygen, fluorine, fluoro. If this kind of species are there in your system, this can easily be attacked. So that's how for the protection case we have oxygen. That's why it is protecting with silicon, and to deprotect them we need F minus or fluoride minus this kind of molecules to deprotect them. So most famous reagent is this one for this kind of protection chemistry is tert-butyl ammonium fluoride. So this one this is used for this kind of deprotection. How deprotection is done? So here you can see normal SN2 type F minus can attack the silicon bond, and oxygen silicon bond can be broken. So alcohol we are generating, what we are needed, and we are generating this particular so silicon fluoro, this particular byproduct, which can be easily removed from the system. So that's how we can do that thing. You can see in presence of acid also we can easily deprotect, because after protonation it can become a good LC or living group, and H2O can again attack silicon, so this can be regenerated. So in with methanol also sometimes deprotection happens. So that's all about silicon based protection groups. Here you can see the deprotection happens in H plus, H2O, and of course N minus. And for the next thing are so rather than oxygen silicon protection groups, another thing is very much famous is benzyl protection. So here you can see the benzyl esters, so benzyl ethers, so they are also used in this type of protection group chemistry. So but this particular protection is very much stable compared to the silicon. So because oxygen silicons are is very easy to keep, because F minus or any H to H plus this kind of condition you can easily protect this oxygen silicon bonds. So let's say we need something very much strong protecting group, because we are using these as our reagent, and we don't want to do the deprotection between these. So then what we need to do, we need to have a strong protecting group. So then we are using benzyles or PMBs, means paramethyl paramethoxy benzyl protection. Uh, this type of things are famous. So so as they are stronger protection group, protecting group, so to keep them also we need we also need some harsh condition compared to silicon. So in silicon, F minus H2 or H plus can easily do the job, but it is not the case for benzyles or for benzyles and PMPs. They are closely related also, so let's just let it be benzyl. So for benzyl reproduction, what we need, we can use hydrogen palladium charcoal. So this is nothing but an hydrogenation reaction. So here you can see this particular carbon oxygen bond. So this particular condition, that palladium charcoal and H2, uh, this particular bond is flipped. Here we generate one toluene molecule, and of course we would be deprotecting and making the alcohol. And HBr can also be used. So you all know the reproduction of ethers, right? So they are all itself HBr is using. So same chemistry would be happening with HBr. So H plus would be protonated. At first this oxygen would be protonated, and then Br minus would attack to the SN2 and to the this particular reaction. So that's how HBr can be protected. So HBr is very strong acid. So that's how your molecule, you need to have some serious acid tolerance. If you have a group which is not this much strong acid tolerant, you would be facing problem to protect this. So then again, H2PD, the palladium charcoal mediated hydrogenation is there, but again, if you have an olefin type of unsaturation in your system, you would be having some problem. So that's how we need to using this kind of protecting groups carefully, looking at what are the possible side reaction that can be happening during the deprotection of them. So that's why there are various protecting group for to tackle the selectivity of other functional groups that are present in your molecule. So yeah, so why I have discussed those, so you can just look at here itself. uh, so you would be discussing more of this kind of silyl oxygen silicon based protection groups and oxygen benzyl protection groups. So that's why I have given a little overview of this type of two important protecting groups. So let's look at this third problem. So here you can see it is what is used, the palladium charcoal paste, right? So we have just shown it can protect only the benzyls, means this type of benzyl ethers. So what, let me write it. So it is OBN protection, right? Benzyl. And what other groups are present? PMB are present. So let me write that also. This PMB paramethoxy, so orthopara. So this is PMB, and this is OBN. And what is TBS? So TBS, I have just told that TBS are uh, the silyl protection groups, right? So TBS would be, let's see, here methyl and here. So this is TBS. So this is TBS protecting group. That butyl silicon. So other is TPTM is same thing. That butyl methyl silane, or that butyl dimethyl silane is just a short form of this TPTM. So from our previous remembering our previous slides, so to deprotect the silicon bond, what we need? F minus or oxygen based thing, or chlorine based thing, or H plus H2, this kind of reactant, or this kind of environment we need to broke this oxygen silicon bond because of its affinity of the electronegative atom. So that's how this can be broken. So to do this we need that, but in this particular condition you can see none of them are there. So that's how we can say this particular OTBS group would be remaining, or this cannot be deprotected in particular this type of reaction condition. So palladium charcoal, what we have shown that with to deprotect this type of this this type of ether linkage, we need palladium charcoal or HBr. Any of the this kind of condition can do the breaking of this ether, this particular ether bond, and can generate or regenerate your alcohol moiety. So let's look at, so you can see the similarity between these. So that's how the palladium charcoal would be. So how the palladium charcoal do? So there are many proposed reaction mechanism, but you can just think of one of so here palladium, so kind of oxidative addition, then hydrogen is there, so this thing, and after that uh, the reductive elimination followed by migration would be generating the weights, and followed by the CH. That's how this deprotection happens. So with this particular condition, this should not be surviving, so it would generate weights, and the byproduct would be OAE and CH3. Again, benzyl will not survive this, and it would be generating the OH, and here this particular toluene type of molecule. So the form product would be TBS would be unreacted, it would be OH, and it also be OH. So now if we coordinate, so things should be C, it also C is right, and here you can see all are, they have to be protected, not right. So it is also not right because PMB group of, should be deprotected in this reaction condition. Again, OBN cannot survive this reaction condition, so that's how C should be the right answer. Now this one, the coming to the next problem. So dibalates. I hope all of you know what is dibalates. So diisopropyl, it is isopropyl group and aluminum. So this is the dibalates monomer form, but it remain in dimeric form actually. So that's how it remains actually. So here you can see aluminium in this particular condition. So it is an dibalate and pretty bulky group because two iso isobutyl groups are there. So that's how it is bulky. So let me write the starting material. So this is our reactant. Oxygen are there, and here there. Right. So one of the unit would be reactant. So again you can see these are not two symmetrical oxygens, because one we have phenyl, one we have methyl. So now it would have some regioselective issues. where it should react with this oxygen center or this oxygen center. So as divalent is used, so you all can always remember divalent would be attacking that side where the steric hindrance should be lesser because it's non bulky. So now compare these two sides. Here you can see we have an very much electron rich electron rich functional group which is phenyl compared to this. So here we have just methyl group. So if so let me write two interactions. So let's say this oxygen is involved at first. Positive charge this and this. This should be generating for one case. Let me write as aromatic. Another possibility aromatic methyl this side. So possibilities are there, but here you can see it would be facing an interaction with this phenyl group. At least it is very much bulky compared to this one. So that's why the system preferred to form this over this one. So this should be formed. Now when this forms, what is happening? It's just like our deprotection chemistry of acetals. So this oxygen lone pair would push and this would do like this. Here we have H, right, and minus. So it should be like this. Now after that, here we have aromatic thing and this particular bond is cleaved. We have generated this particular product. Now what should be happening? So it can neutralize this H minus can attack and this can be open up. So it would. So let me clear this part. So it is well understood now. It can be candidates. So after this attack, here it is reduced by the hydride group, aromatic ring is there, hydride is there, and in H3O plus this particular acidic condition, this oxygen aluminium bond can be clipped. So here we are generate OH, and here this. So now if we compare with the possible things, so it is matching with A. That's how we can say A would be our right answer. So if we look at that other things, you can say if we do the other thing means that is just we attack from the uh, uh, hinder side one, then we would be generating B. So that's how we can do the. We can discard this option. Here you can see both are protected, but this particular you can just see this is PMB protection. So if we want to do that, what we'd be needing HBr kind of strong acid we should be using, or the palladium charcoal hydrogenation. So any of these condition can do the PMBD protection, but here the condition is only H3O plus and divalent. So both the protection is not possible and none is okay. So that's how the A would be the right answer. Now coming to the next one. So here you can see this symmetric one, and it is almost similar to our previous approach molecule, but one thing is here this kind of things are used which are So stereochemistry would not be factored here because here you can just see it is, here you can pass up this plane, so it is on symmetric manner. So both oxygen are in same environment, so any of the oxygen you can choose. So LCl3 would be reacting with this, so this thing would be forming, then the same protection chemistry of ketals. So we have generated this kind of thing, OLCl3. Now LiLH4 is an source of hydride. Hydride is donated like that, and this thing is generated. And though it's this kind of thing is will not be surviving much in the reaction medium, so it should be generated. Now here we are doing the PH3THF. So I think all of you know the base treatment. So this kind of approach, here we are having BH2, and this is now become saturated. Now this pH can be easily converted to alcohol with H2O2 condition. So the final product that we would be getting should be this particular. So now let's look at the, so A, the ketal is acetal is unaffected, so it is not. D also again you can see they have do the benzyl deprotection, but this condition cannot do the benzyl deprotection. We will be needing palladium charcoal mediated hydrogenation on HBr. So not correct. So here you can see this correct because ODN is still there and rest of the things are weak. So 3, 1. Here we have one, one carbon I have missed. So there should be 3 carbon, and that's how C would be the right answer. Now coming to the next problem. So Hg2 plus, here you can see the some pre-protection chemistry and protection chemistry is involved here. So Hg2 plus, what Hg2 plus would be doing. So this first problem I itself discussed. So I hope all of you can easily do that. So the sulfur Hg bond, that tendency, this particular protection would be happening at first. So TBT, PS, so nothing but it is just TPS protection. H2PH, presence of this Hg2 plus, this bond and sulfur would be doing this elimination, and ultimately here we are generating what? Aldehyde center. Aldehyde center we have generated. Yes, so after step A, this should be our product. Now they have done in a BH4 treatment. So what it would be doing? So in a BH4 would reduce this aldehyde to its alcohol form. So 1, 4 carbon should be there. 1, 4. Here we have the TPS protection intact. Benzyl thing is also there. Now with mom chloride triethylamine. So this methoxymethyl mom protection, this particular thing triethylamine, what would be happening? This way it should be proportionated. O minus can generate. This attack is feasible. It would generate O mom protection. Some would occur here, and your product would be this. Now if we compare, it should be right answer. You can see other options also. So two mom protection centers. It is not possible as TPS for TPS protection. What we need, any fluoride source should be there, but here it is not. That's why it is not be protecting. So it's not correct, and Hg2 plus this should be protected first. So that's how you can easily solve this, and this should be your answer. Now coming to this, here PMB protection, parabethoxybenzene, so let me write that. So we are using this kind of bromide or chloride. Here you can see two protection groups are there, and hydrogen, and as a base we are using sodium hydride. So they have asked me the base reagent to carry out this transformation. So let's look at. So when sodium hydride is charged in this particular uh, reactant at first, we say proton, acidic proton would be taken by that, and O minus would be generating, and then a simple SN2 reaction. It's bromide version, chloride version, anything you can do to do the PMB protection, well known chemistry. Right, so for PMB protection, this particular reaction condition is generally used. So if that happens, O CO2. So it can we can generate for A case and B case. This happen for, let's say, for C case what is happening. So this particular condition PMB weights means here we are using alcohol. This is we are using, and another reagent is this. So now in basic media minus is generated. Here it is attacked. So OMe H2O, here C, let's say double bond NH, and here we have CCl, right? So this we have generated. Now we have also PTS, one acidic reason. So this nitrogen can be protonated in the acidic form, and it becomes this. Now we can think of this alcohol, our starting with. So this is an electropositive center. Now SN2 can happen. An alcohol can attack this center, fall. followed by this type of thing. So here again we are generating PMB protection. We are again in the same, not same way, but we are generating PMB protection. H2O. So you can see for three cases A, B, C, we are generating the same this protection, but they are asking about the best reagent. So how we can do that? Or we can choose what would be the best. So you can see here we have anhydride and here we have acidic alpha. Here you can see the stereochemistry is intact, means we need to maintain this particular stereochemistry. So this is an chiral molecule. But when we are using this kind of strong base in equivalent amount, but equivalent or generally more than one equivalent can be used are used. So then this particular acidic proton can be taken, and this kind of species can be generated. Now when this kind of species generated, this would lead to racemization, means if these two condition you are using here, you can generate plasmids, or not purely racemic, but of course one uh, both the isomer or both the R and S you would be getting. So that and why is that? Because of use of this particular strong base. But you can see in that particular this C condition where in each use of this particular strong base is minimalized. How it is because it is in 5 mole percent only. So here we are using this to generate this strong or very much good living group. So this living group, the living aptitude of this is so high that just alcohol from itself can attack this and do the substitution reaction and make the OMB protection. So for that, to minimize the racemization, this particular condition C would be the best choice. So so in the particular question that's they are want to check. So this racemization concept. So that's how you can say that C condition should be the best for this kind of transformation where the chirality is involved and you want to uh, make make your molecule in make the molecule chiral, or you can uh, make this chirality intact in this kind of condition, and the other condition it will be racemized. But let's say if you have a molecule where no chirality or chiral center is there, so then you can use any of them. But for this case, as here we have an alpha proton which is acidic, thus alpha to the ester, so that's why this racemization concept comes to play, and you be racemized if this particular condition are used. So moving to the next problem. So TBSCL, right? So this is TBSCL. If we react, so here you can see it is used in one equivalent. So midazole used as base. So two OH are there. So they are almost identical. So both OH can be protected, right? So the product would be one case this these two are the possibilities. Now just one from here to here, how we can do that. So let's say here we have an axis and we just rotate the molecule 180 degree over this. So if we rotate this, so this below hydroxy would come above, and above OTBS would go below. So these two molecules are nothing but homomers, means they are same molecule. They are not enantiomers or diastereomers. They are same. So that's now check. So yeah, A, B should be the right option, and yeah, A, B both are identical also. So we cannot choose just one. So A, B and both are identical, means they are homomers. That's how the right answer should be. So that's how you can little bit stereochemistry is involved here, and if we uh, solve, or if we care about that, we can easily solve this kind of problems. Moving to the next problem. Here again you can see TDSL theory is used for the protection chemistry. So what is TDSL? This particular now. So again we have two possibilities, and let's generate two isomers. Then we will be checking the stereochemistry. OTPS here is unprotected. You can see one equivalent, so that's why one of them will be protected. Another will be this. So now what are this? These are actually enantiomer, because you can think of one mirror over here, and so these two are enantiomers to each other, and the possibilities are like this. So if we rotate and want to go back like that, it would be again this below. So they are not homomers. So they are enantiomers. So the right answer would be enantiomeric monotropic. They are not diastereomers, not same homomer. So here one interesting thing you can observe. So this is a chiral molecule. Let's say it have plus rotation. But when we would do the reaction, anyway this this is not reacting, but the system we are generating two enantiomers. So from a chiral molecule we are generating racemic compounds. touching, but this type of two selectivities, this way and this way will lead to racemic mixture. So that's how also the molecule can be racemized. It is a kind of observation. So you can do this type of things. So this is just a simple problem, but you can see that how the one chiral molecule is being racemized without touching the particular chiral center. So answer would be B. Enantiomer 2 degrees plus. Coming to the next problem. So here they have used an chiral catalyst and acetic anhydride treatment. Non-selective desymmetrization, selective desymmetrization, or a chiral desymmetry. So a chiral is not, so it is a chiral center is there, so should be the selective or enantioselective. So we so let's say it is in racemic form as it is racemic, and here we are generating receptor. So when it would be gastrioselective, if one more chiral center is present, then only we can do that. Otherwise, it is enantiomer. Because why is that? Because here, if no chiral catalyst is there, only we do this acetic anhydride treatment. I think the prompt product would be this and ethyl below is hydrogen ion. So it is, if R it is, so it is enantiomer. Let's say here if we have an chiral center, then only we can say it is diastereomer, because then it will be RS and let's say it will be SS. So then it will be diastereomer. But here only one chiral center is there. That's why it is enantioselective, we can say. So here also let me try something. So let's say we have an chiral molecule, right? Then we are comparing to the previous problem. So let's say we have this particular molecule, chiral molecule. Let's say it is plus. Then we are doing acetic anhydride treatment, one equivalent. So two possibilities are there. We would be generating this compound and this compound. Then you can see these two are enantiomers. So without touching the chiral center, we are making a racemic mixture of an chiral molecule. So again, the same thing would be happening if we do not use that. chiral catalyst. So that's why to maintain the stereochemistry or to retain the stereochemistry, let's say it is a, so if we do not use chiral catalyst over here and do the protection of acetic anhydride, this chiral molecule would be racemized without touching the chiral center. So this is one of the things. So that's why in chiral catalyst we are doing the enantiomer selective decimation. So which kind of catalyst can be used? So here, so I have to check how can what chiral catalysts are used for this type of protection chemistry, and then I can let you guys know. Now again the protection group chemistry thing here. So all you can see, just let me write the protection groups. So TPTPS, so it is nothing but this dimethyl tadbutyl silane, this particular protecting group TPTPS, or in short you can say TPS protection. Another is TMS, trimethyl silane, and another is TIPS, isopropyl. So you can see all three protection groups are silicon based, and just we have read, or I just can give a brief overview of that. So the protection chemistry. So if we, let's say we have this kind of alcohol and bromine. So and we only want to do substitution reaction over this. So then we are using this kind of lithiated species, but we do not do the use protection group. What will be happening? So this lithiated species would take this acidic proton first, and it would be quenched, and it would generate this acetylene molecule. So to minimize that, we just protected this with this TBS protecting group. In presence of imidazole, it can be easily protected because this type of silicon molecules have high affinity towards electronegative elements like oxygen, fluoride, and fluoride. So that's why this kind of protection groups are used. So they can be make is they are can be made easily because of this oxygen silicon bond, this particular tendency to form this particular bond, and also they can be easily broken also with F minus and fluoride minus or fluoride minus or fluorides. So that's how protection groups of silicon based protection groups are used, and the most, yeah, so this kind of butyl ammonium fluoride, this kind of F minus source are used to protect this kind of things. So how it is happen? So F minus can easily attack the silicon center. So you can see over here its strong affinity towards electronegative elements, and fluoride, you all know how electronegative the fluoride is. So that's why this particular attack is favored, and then if this happens, oxygen silicon bond would be killed, and we would regenerate our alcohol molecule, and this byproduct can be easily removed from the system. So that's how the protection group reprotecting chemistry works. And you can see the acidic condition you can also use, and chloride can also be used sometimes. And here you can see H3O plus. So at first this particular oxygen is protonated with H plus, then H2 in acidic media, so we are using aqueous acids. So then H2 can easily attack the silicon bond, and then this particular oxygen silicon bond can be broken. So that's how the protection works. So coming to our current problem, yeah. So here you can see all are silicon based protection groups, and here we are also using the F minus in excess amount. So here we can think of an global deprotection, as all are silicons, and F minus is also very much excess. So all protection groups can be flipped, and we will be generating some the all the protection are will be done, and alcohol moiety will be regenerated. So your product would be this kind of thing. So if you can correlate, C should be the answer. Oh, D would be the answer. Because C, you can see this protection are still there. So you can see the other options where some protection groups are unreacted, but just a minus condition, it can be happening. All should be protected, and that's how it should be your answer. Now to carry out this particular transformation, what should be the right reagent? So let's look at the protection groups first. So PN, all of you know, PN is openzyl, mom is this kind of thing. Another thing is PMB. PMB would be paramethoxy. This, and another thing is TPS. So TPS is so that butyl is there, methane. So this is TPS. So now we are want to just uh, selectively deprotect the TBS only, and we want to keep the other things intact. Here just we can see. So how we can do that? So just today's lecture is mainly focused on these things only. So F minus can just do this, because F minus can selectively clip oxygen silicon bond. So if you check other things, so here acidic condition is used, here the B should be your answer. So to deprotect this. So now look at the other conditions. So let's say this condition is palladium charcoal. So what would be happening? So O benzyl, this can be deprotected, and PMB it also be should be deprotected, and these two would be unreacted. So if this palladium charcoal condition we use, our product would be this, and here OTPs. So if condition is used, this should be our product. And in acidic condition, what it can be happening, so the mom, this can be detected. So then our would be here, the TPS should be unrelated. So you can see how different condition we can just manipulate the system and detect the different things. So that's how you can think of how use of different protecting good can be useful. Let's say I want to do the chemistry only to this center, then I would be using fluoride minus. If I want to do chemistry over this and this, then palladium charcoal can be used. If this I want to do, then PTSA can be used. So that's how we can just different condition and selectively we can protect and do the chemistry. So that's how the protecting group chemistry came handy in the natural product synthesis or any kind of synthesis you can think of. So that's how they are important. I hope this is you have understand. So this is the next problem. So again, it's just a mom protection thing and triethylamine and two equivalent. So here the question is the selectivity, the primary alcohol versus secondary alcohol, and here you can think of you can just think of the steric interaction. So uh, compared to secondary and primary, this particular which is more prone to attack and molecule over secondary alcohol. So that's how triethylamine and this particular reaction condition only primary, as it is used in one equivalent, only primary alcohol would be attacking and do the protection chemistry. So let's look at the mechanism. So mechanism is very much simple, just an SN2. So in presence of base, O minus can be generated. Particular kind of elimination would be generating this particular compound. Oh, sorry, no, clean this. No saturation is there. So this should be our product. So if we compare, it would be C. This should be we are finding, and we can selectively protect the primary alcohol over secondary. So this is I think, yeah, today's this should be our last problem, and let's look at. So again you can see this is primary alcohol and this is secondary, and in HTBS same condition. So the steric interaction would be the factor over here, and the primary alcohol would be protected over secondary. So here it would be TBS. And now this is the condition. You all know that is just an oxidant. It can oxidize alcohol to keto or aldehyde. So here it is secondary. So it would be keto and this. So let's deal with the answer. Yeah. So that's how you can easily solve this kind of problems, and that's how the protecting good chemistry came handy to do this type of regioselective reactions also. So if you have any question, you can ask, or I want to keep some photosynthesis some literature you would want to discuss. So we have half an hour time, so that would be enough. Yeah. So seems like you have no questions, so let me give a literature thing. So I would be discussing total synthesis of total synthesis of this particular molecule. So this, although it is not an natural product, you can so it is not isolated. So but so there are some interesting features of this kind of molecule. So one another thing is that this kind of this particular molecule is synthesized by one of one of the Indian scientists, one of the great Indian scientists, which is none other than Professor Govardhan Mehta. He had synthesized it in 1987, long back, and this was published probably in Jax 1987. So, although it is it have no biologically active properties as such, but this kind synthesis of this kind of molecule is uh, very much tricky and very much interesting also, because you can see the point two for this particular molecule is 52H, and this is this homo hexaprismin type of molecule. For the importance, so this can be useful syntheons in the design of synthesis. So you can see so the when we do the retrosynthesis, we generate some synthon. Of course, they are not biologically accessible, so they are completely our thought frequency. So to do that kind of synthesis, this is very much related to that also, because it's an imaginary molecule. So just that we can make. So if we make this kind of molecule, so that's kind of a challenging symptoms we also can think of. And the and another thing is high energy materials and supramolecules. So they are not only the biologically active molecules are used. There are go creative as much you want. So if you are creative and your system permits you have an better having a better property of supramolecules and materials, why not? So for that kind of cases, this type of synthesis is very much useful enough, and also this type of rigid carbocyclic framework synthesis is really challenging. And one more interesting thing about this kind of molecule and this name, this gadurine, how this came. This is nothing but came from the gadura, and so our Hindu demigod, you all know probably, this is the Bahana of Lord Vishnu, and uh, so from from the naming of Garuda and similarity of this form for structure and the structure, then in particular this name Garudain is given, and so there are so outside the synthesis, we all know the importance of Garuda. So we have an in the Indian Army itself, the brigade of Garudas. There we have backs for Garuda, and the other countries like Indonesia, you can see the similar structural features of Garuda. So that's how the naming and the some thing is there also. And now look at the stereochemistry. So this synthesis of this kind of molecule is not new. So many active groups are there who are working this type of areas. So these are some theory family of theoretically interesting. So they are not isolated from nature or something, but they are just thought-driven things. So theoretical thing like uh, this sonutane. Here you can see this kind of complex structural scaffold is there, where we have this this rigid thing, and it is also connected to this very much rigid system, but people have made this basket in one of the famous one. There you can see it has resemblance with the basket, right? So resemblance with baskets. So that's how it is basketed. It is again an prismen type which have this type of terbutyl groups with 4 carbons, rocketed because of similarity of rockets, and cubane. This is our gadurine which I am going to discuss. This is dodecahedron, and this is also leucodane type of molecule. So there you can see there are various molecules of them. Many of them are synthesized, and some of them are not addressed yet, but they are structurally very much intricate. So now synthetic challenges with gadolinium. So in this family, one thing you can of course say, let's say if we do the 2 plus 2 cycloaddition of this type of rigid molecules. So if we do that, there are various possibilities. One possibility is that this 2 plus 2. In there itself we have two possibilities. Not two, there are many possibilities are there because of the alignment of them you can see. So this and this order is their stability order, because you can see here the steric interaction is minimized. So this is more stable. Then this is little bit less stable than this. Then again this, it has some interaction, and here it is more, it has more interaction, and when we come to this, it is most unstable structure of 2 plus 2 cycloaddition of this type of molecule. So you can see this normal 2 plus 2 if we do, we definitely not going to make this kind of molecule. So making that itself is challenging, and then again we need to do the 2 plus 2 to make the gadolinium. So again, excuse me, 2 pi and 4 pi cycloaddition would be generating this kind of 7, 8, 9, 10, which are definitely not related to gadolinium. So just discarding, and 4 pi we can think of. So these two ends, if we do, actually not 4 pi, 2 pi simultaneously. So this kind of 4 pi, that's it, 2 pi. 2 plus 2 cycloadditions would generate. So among all the structures, this gadolinium is most symmetric one. So that's why the, you all remember the point group would be D2H, right? And so from this slide you can say how much challenging it would be to synthesize that. But Mehta in 1980 come with an interesting electrosynthetic approach where he thought of doing 4 plus 2 followed by 2 plus 2 to make this type of molecule. And here you can see we have disconnected this and this part. So if we do that, here we will be generating one cyclobutene and here cyclopentadienes, two cyclopentadienes, this. And so with normal 4 plus 2 should be difficult because you can see both are electronically same. So diene and dienophile, this choosing this selectivity, what would be diene and what would be dienophile would be difficult, and synthesizing this is also challenging. So to access these as a dinophile, he just modified this. So if we have this kind of thing, now it is, this should be diene, this is dinophile because it is electronically poor because of this type of 2 keto are there. So electrons are like this or this, so that's why this electron poor and this electron this, so this should be at normal demand disorder. So that's how you want to bring the selectivity and make the folder faster. Now let's see how we have synthesized. So we have synthesized so cyclopentadiene and this hydroquinone. This type of molecule. So it is dienophile diene. Uh, 4 plus 2 cycloaddition is happening and generating this. So let's do the 4 plus 2. What is happening? This we will be having this, and then we need to have double bond here. So that's why it is 3 steps. So let's say we incorporate one bromine over here or any dipping group, and then we do the elimination. Then again we generate the double bond over here. That's how we can do that. That's why it is 3 steps. So alpha formulation just we need to then do the elimination to generate this. Now after that again one cycle addition 4 plus 2, 2 4 plus 2. So it is dienophile, it is diene. So same way this should be our thing. So this is generated. Here you can see the reactivity also, how much fast it becomes due to this kind of structural management. Now this thing happens now with TiCl3 acetone. What they have done, so selectively they have to the electron transfer of this electron core double bond over this to our electron rich, this is electron core, so electron will be attacking this and reducing particular this type of double bond, and it will be generating this type of molecule. Now when it is generated, you can see the proximity of these two double bonds are pretty, and they would tend to do 2 plus 2 cycloaddition reaction. So there itself this reduction, it is stereo selective because you can see it is one of the enantiomer and another enantiomer would be these hydrogens are below and this particular ring would be above. So that's one of the other that stereomer. but this particular condition they have optimized, and this particular diastereomer would be measure over that. Now the HBO condition, they have done the 2+2 cyclization. So now for membering from like this. Now in BSC-IBM treatment, they just do the one alpha halogenation. We just can say alpha bromination they have done. So here you can think of that why only this side. So you can see this is itself an symmetric molecule. All these four centers are identical to each other because you can think of two planes actually. That one plane is there cutting in between, and another plane you can think of which are going to keto. So as two planes are there, you can say these four carbon centers are identical, and when we do the one bromination, any of the side would be the same as all are identical, and we can generate this one. And second bromination, to minimize the interaction between this, the most favorable bromination would be of course there. This is also what thing happened. Now in which condition we all know this is just an Favorsky, this elimination followed by this member formation and ring contraction. So Favorsky well-known reaction they have all done, and this is ester they have generated, or acid you can say, two acids or esters they have generated. So from esters with this condition they have generated acid, then they have is methanol mediated hydrolysis they have done, and finally unsticker condition they have incorporated brom again to bromo they have incorporated, and with lithium THF that butanol condition halogen lithium halogen exchange followed by protonation, just like that they with the incorporated the remove the bromines and incorporated protons. So that's how they have done the completed the synthesis. So um, this is that's how they have completed their synthesis. So this is 87 done by Mehta, and one of the other figures for this type of drug synthesis field, and I hope all of you understand this well, and you can see the power of the retrosynthesis also. In compound, any theoretical compound you can take and do the particular or well retrosynthesis analysis and do the reaction just like that. So that's all for the today's class. If you have any question, of course you can ask. So yeah, so this simple Fibroski type here. Let me just draw that. So normal Fibroski you remember, right? Just wait. Yeah, so let's I am just writing, let's say, this 7-member thing. Huh? 7-member ring. So here one side we have two. Now let's say we uh, in any ready base acidic proton would be taken. So acidity be, yeah, that's, oh, you asked earlier also. So let's say, yeah, so this H and this proton, which is more acidic, let it be this. If we do that, what would be the next reaction? Nothing. that happens also. Let's say we have taken this proton and generated the enolate this side. After that, ask the which is the suitable condition. It would be the weak one, and so C would be the right option. Now you just watch that every every problem, today's problem are correlated with each other, because just you can see with the first problem your product is uh, this, and it is the starting material for the next thing. So it goes on, this continuation is there up to this point. And so why it is that? Because it is part of one photosynthesis of Rishutin by Tashuta and by Tashuta in 1979. It is published in JACS. So they are here followed the same thing. So up to this point, it is in the question, and after this, it is kind of new, which is not included in the question thing. So after 2 plus 2 cycloaddition, this particular 4 member ring is formed. Now NaBH4 reduces this, so it selectively approaches from above the side. How you can explain that? Because here you can see the compound is kind of like this shape, and so this is the concave shape actually. So from concave face the H minus is approaching, and concave is stereochemically not approachable, or it faces more steric interaction. So that's how this particular diastereomer is a major amount. Then again, this parts are covered in question, and then with this the docile protection they have done. So how the reduced selectivity came? So this is the tertiary and secondary. So between these two particular alcohol, secondary alcohols are prone to more attack or fascicular attack. So that's why this. Now with K2CO3, at first we generate O minus. Now this particular thing attacks this particular carbon center, followed by this particular shift. So in that way, this particular 555 system is formed. Now then zinc iodide would make this as carbon-carbon double bond, followed by this reprotection. Then again these parts are covered in question, all the parts are covered in question, and they have done the Rishutin synthesis. So this should be the last problem, or not last problem, last class, today's last class. But one thing you just notice, how this simple transformation lead to this complex molecule which is shooting. This is just total synthesis of shooting, and the assignment problems are just related to that. So I think one this I should explain in today's class, which is the total synthesis by Mehta. So this is again synthesis by Mehta, and I think many of you know him. He is one of the great Indian chemists, and Govardhan Mehta, he have done this particular total synthesis. So how he have done that? So with this cyclopropene and this particular thing, so it acts as diene, and this is dienophile. So in the product it is forming due to the secondary orbital interaction. So kind of uh, this kind of thing forms due to this secondary orbital interaction. Endo product is major. So with each new, so here is heat. With each new, the 2 plus 2 cycloaddition, here 2 plus 2 cycloaddition from this compound. Now the retro 2 plus 2, it is done like this, the retro 2 plus 2. Now to invert this particular stereochemistry, this reaction condition they have used, and got this, then hydrogen palladium reduces these two double bonds. Here you can see. Now this reduction they have done. No, with methyl iodide they have incorporated over here, and this B product it forms because of this particular reflux condition selectively this geminal dimethyl. Now with this Wittig reaction, now with LH they have done the reaction, and this is also part of kind of we have discussed button may combi precursor formation and its and final removal of this xanthate ligand. So that's the synthesis by Mehta. It is his shooting, and you can see just 10 steps we have completed this. And for the previous report, one of the previous report, the Shata, it have taken 20 steps. So we have successfully incorporated some of the heat and age group. So most sustainable reagent we can say of the nature, heat and light. We have incorporated that and minimized steps to 10. So one of the great synthesis of the Mehta. So I think if you have not any question, I think yeah. So in this high point, we think we can end our course of here. So all of those who have joined until now, thank you for that. And this is one of the great synthesis actually. And here we are just ending our discussion of this course. Study guide to retrosynthesis. So, who have stayed and joined up till this 12th session, thank you for that. I hope I am able to convince how this strategies, this little conversion, little transformation thing are very much useful to when you are getting a challenge to make this kind of complex molecule. And I hope who have taken this course will help in their future. And thank you all for joining. And so I am Sinandi, your TA for this course, and now I can just sign off. And thank you all who have joined.